In this video, I am going to show you how to write or find or determine the electron configuration of all the elements of periodic table. So let us write the electron configuration of phosphorus first. You know that phosphorus has atomic number 15. This means that phosphorus has 15 electrons and 15 protons, right? That is, atomic number represent the number of electrons in the element. So how to distribute these 15 electrons of phosphorus in different subcellular orbitals? So electron will be distributed to different subshell or orbitals according to energy, right? So look, 1s in first energy level we have just one subshell, that is 1s, and in the second energy level we have two subshell, 2s 2p. In the third shell or energy level we have three subshell, 3s 3p 3d. In the fourth energy level we have four subshell, 4s 4p 4d 4f, right? So look, S subshell can take maximum 2 electrons, P subshell can take maximum 6, D subshell can take maximum 10, and F subshell can take maximum 14. So the energy of 1s is less than 2s, right? Look, you know that the energy of subshell can be determined by the n plus L value, right? Look, this is your nucleus and this is your first energy level. The first energy level can be identified by the principal quantum number n. For first energy level we will write n equal to 1. For second subshell we will write n equal to 2. In first energy level we have just 1s for first energy level we have just one subshell, that is 1s, and for second energy level we have two subshell, that is 2s 2p, right? And for third energy level of subshell we can write the value of n equal to 3, and here we have 3s 3p 3d, that is in third subshell. In third energy level we have 3 subshell. So the SPDF, right, this subshell can be identified by the value of the quantum number, azimuthal quantum number. For S we write the value, for 0 we designate the subshell S, for 1 we indicate P, for 2 we indicate D, and for 3 we indicate F. For the value of L equal to 0 we consider S subshell, for the value of 1 we consider P subshell, and for the value of 2 we consider D subshell, and for the value of 3 we consider F subshell. So which subshell has more energy? So between these two subshell, which has the more energy, we can determine the energy of a subshell by the value of n plus l. For 1s, the n plus l value is for here 1 is the principal Compton number, that is 1. For s we 0, so 0. For 1s we get n plus l 0, and for 2s we get 2 plus 0, that is 2. So look, so the value of n plus l is greater for twice s, so twice s subshell is more energetic or has more energy than 1s. So this is the basic idea, and I would like to also give you more basic idea so that you can have clear knowledge, right? So look, s subshell start with 1s, then we can write 2s, 3s, 4s. P subshell start from 2p, then we write 3p, 4p. D subshell start with 3d, then we like 4d, 5d, and F subshell start from 4f, then we write 5f, 6f, like this, right? Okay, so to write the electron configuration of phosphorus, look, we can simply draw like this. We like line like this, 1s, and s subshell can take maximum 2, then we can write this 2s, 2, then like this 2p6, that is here 6, 8, 10, then 3s, 2, 12, right? After 3s we have like this 3p, 4s, so 3p, right? 3p, so 2, 4, 10, 12, then here 3. So now we have 15 electrons, 2, 4, 6, 10, 12 plus 3, 15. So this is the electron configuration of phosphorus, right? I think this is the first method. You can also write this this Aufbau principle like this. Let me delete this, right? Look, you can write like this: 1s, then 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, right? S can take maximum 2, P can take maximum 6, D can 10, and F can 14. So like this, right? Like this. Okay. So now I'm going to show you the second method to write the electron configuration of phosphorus. So in second method, you have to memorize the orbital sequence, right? Like this. This is the orbital sequence you have to memorize. SS, like this. SS, PS, PS, SS 1 times, PS, PS 2 times. Then you can write PS, PS, then you can write DPS, DPS, the 2 times, then you have to write FDPS, FDPS, and this will continue, right? There is no limit for FDPS, but you have to write SS, PS, PS, DPS, DPS, FDPS, FDPS, FDPS. You have to memorize this. Here is the easy way to memorize this orbital sequence: SPDF, right? Look, at first you have to take a S, and write S twice, SS. Then you have to consider PS, right? Consider PS twice, PS. Then you have to consider D. So write D, DPS twice, and then you have to consider FDPS. You can take any number of FDPS according to your need. FDPS. That is easily you can remember this SS, PS, DPS, FDPS. So here you have 15 electrons. You know that S can take maximum 2, P can take maximum 6, D can take maximum 10, and F can take maximum 14. So let us distribute these 15 electrons: 2, 4, 10, 12, plus 3, 15. So we don't need this subshell. Now we have to place the value of principal Compton number. You know that S subshell start from 1s, 2s, then 3s, 4s, it will continue. P subshell start from twice P, then 3P, 3D, 3P, 4P, right? Then F subshell start from 4F, 5F, 6F, and it will continue. So let us first place the number before S: 1s, 2s, 3s. P starts from second shell, that 2P, 3P. So this is the electron configuration of phosphorus according to the our second method, you can say. So now I will write the electron configuration of phosphorus using noble gas notation. That is, what is the noble gas shorthand electron configuration of phosphorus? You know that noble in the periodic table you have in group 18 you have helium, neon, argon, right? Helium, neon, argon, xenon, right? The atomic number of helium is 2, atomic number of neon is 10, argon is 36, and xenon is 54. So to write the electron configuration using noble gas notation or shorthand, you have to consider that noble gas that has atomic number immediately lower than your target element. So phosphorus atomic number is 15. So we have to find out the noble gas that's atomic number is immediately lower than 15. So this should be neon, its atomic number is 10, but if you consider argon, that is 36, that is higher. So neon is the best element, right? So let us count this 10 electron: 2, 4, 6, 10. So this is the electron configuration of neon. So write neon like this. Then you have this 3s2, 3p3. So this is the noble gas electron configuration of phosphorus, right? Okay. Now I will ask you a question: how many valence electron does phosphorus have? So from the electron configuration of phosphorus, you can easily find out the valence electron of phosphorus. Look, for finding valence electron, you have to find out the valence shell by looking the value of m. Here highest value of n indicate the valence shell. So here the highest value of n equal to 3. So here 3 is the valence shell, right, or outermost shell, or or highest occupied energy level. So for n equal to 3 we have 2 plus 3, that is 5. So phosphorus has 5 valence electron, right? Balancing electron are important, right, to form bonds. So look, phosphorus is a non-metal, so it has 5 valence electrons. So to fulfill octet, it will share 3 electrons, right? That is, it can in ground state electron from ground state electron configuration of phosphorus, we can say that phosphorus can form 3 bonds, right, to satisfy its octet. So now I will show you the orbital diagrams for phosphorus. So you know that S subshell, this is 1s. S subshell has 1 orbital, so we will write 1 box. 2 subshell also has 1 orbital, we will write 1 box. P subshell has 3 orbital, so we can express 3 orbital considering 3 box for twice P. Then we have 3s. So s orbital has one orbital, that is 1 box, 3s, right? Then we have 3p. You know that p subshell has 3 orbitals, so we need 3 box. So in s subshell we have 1 orbital, so here we are giving 2 electrons with opposite direction. For 2s we'll write 2 electrons with opposite direction. 1 electron will spin in a clockwise direction, another electron will spin in anti-clockwise direction. For twice p we have 6 electrons, so 2, 4, 6. For 3s we have 2, but for 3p, look, we have 3 electrons. But if I place this 3 electron like this will be wrong, right? Because you know that electron repel one another. So at first, since this 3p subshell has 3 orbitals, which are called degenerate orbital, that is, the energy of these 3 orbital is the same. These are the degenerate orbitals. So every orbital will take one electron before pairing up. So here we have 3 electrons, so every orbital at first will take 1 electron, then it will pair up if you have more. So there is no more, so they will stay like this. Look, here the direction of spin is the parallel, that is similar, right? It will spin like clockwise, it will also spin in clockwise direction, right? The spin will be same for all the electrons in a degenerate orbitals. So this is the orbital representation of phosphorus. Now I would like to ask you a question. How many lone pair electrons, how many unpaired electrons does phosphorus have? The number is 3. So these all are paired electrons, that is 2, 4, 6, 8, 10, 12. 12 electrons are paired electrons, but 3 electrons are unpaired electrons. Now I would like to give you the idea about paramagnetism and paramagnetic and diamagnetic substance. Since phosphorus has unpaired electrons, so this is paramagnetic, and in diamagnetic substance you don't get any unpaired electrons. Since phosphorus has 3 unpaired electrons, so it is paramagnetic, right? Now I am going to give you more information from this electron configuration. Can you tell me how many s electrons does phosphorus have? Look, phosphorus has how many s electrons? Look, in s, here we have 2 electrons, then 4, then 6. That is, we have 6 s electrons, right? Then we have how many p electrons in phosphorus? So here we have 6, and here we have 3. That is 6 plus 3, that is 9 p electrons, right? So now I am going to tell you about the core electrons and valence electrons. Look, in phosphorus, what is the core electrons? In phosphorus, the valence shell is the third shell, and after valence shell, before valence shell, you are getting this. So this is the core electrons for phosphorus, and this is the valence electron. That is, without valence electron, you will get core electrons, right? So now I am going to give you this is the electron configuration of ground state for phosphorus, but what is the electron configuration of phosphorus in excited state? So in excited state, look, the electron from 3s from 3s will go SSPS space will go to 3s 4s, right? This is like this. So in excited state, phosphorus will have 1 to 5 unpaired electrons. If you draw the orbital diagrams, then you will get 5 unpaired electrons for excited state. You know that from electron goes from lower energy level to higher energy level after absorbing energy, but electron comes from higher energy level to lower energy level after releasing energy as light, right? Okay, now let me tell you about the electron configuration of phosphidine. So what will be the electron configuration of phosphidine? You know that to write the electron configuration of an ion, always you have to think about the neutral atom. So in a neutral atom, phosphorus has atomic number 15, that is, it has 15 electrons, and for these 3 charges you need to add 3 more electrons. That is, in phosphidine you have 18 electrons. Now write the orbital sequence: SS, PS, PS, right? Then you need to write DPS, DPS or FDPS according to your need. So 2, 4, 6, that is 10, 12, 12, then 12 plus 6, 18. So we don't need more. So S start from 1s, then 2s, 3s, P start from twice P, 3p. So this is the electron configuration of phosphide ion. right? So if you draw the orbital diagram for phosphidine, then you have to draw like this: 1s, then 2s, then 2p, then 3s, then 3p. For 1s, you have to place here 2 electrons with opposite direction, and 2p you have 6. So you know that every orbital can take maximum 2, right? 3s. And for 3p6, look, at first you have to place 1 electron with parallel spin, then you have more 3, then you have to pair up with opposite spin, right? So this is the orbital diagram, and there is no unpaired electrons, so we can say that phosphide ion is diamagnetic. Okay, let us consider now this element, aluminum. Can you tell me what is the atomic number of aluminum? The atomic number of aluminum is 13. So it has 13 electrons, right? So how to distribute this electron? So we know this sequence: SS, PS, PS, then DPS, DPS, FDPS, FDPS, FDPS according to our need. So S can takes maximum 2, then 2, 4, 10, 12, 12, 13, right? So we don't need this. So S start with 1s, 2s, 3s, P start with 2p, 3p. So now we have 13 electrons, right? Okay. So how to do the electron configuration of aluminum 3+. You know that to write the electron configuration for ion, we always think about the electron configuration of neutral atom. In neutral atom, aluminum has 3 electrons, as its atomic number is 13. But for 3+ means you have to deduct 3 electrons. 3 electrons. That is, you have now 10 electrons. So for 10 electrons of aluminum, how to write the electron configuration? So at first you have to write the electron configuration of neutral atom, then you have to subtract 3. So the electron will be removed from the outermost shell. So 3 means you have to replace 1, then 2, that is this. So the electron configuration aluminum 3+ is 1s2, 2s2, 2p6, right? So what will be the orbital diagram for aluminum 3+? So look, 1s, 2s, and 1s, 2s, 2p. So 2, 2, 3, 4, 6, right? So this is the orbital representation, and since there is no unpaired electron, so we can say that this is diamagnetic. This is Al3+ is a diamagnetic ion. So can you write the electron configuration of this cobalt? Cobalt, the atomic number is cobalt is 27. This means that it has 27 electrons. So how to do the electron configuration? So look, 1s. At first we'll do this method, 1s, 2, then 2s, then 2s2, then this 3s2, 2p6. So we have used here 8, 10, 12. Then we have 4s, 3p, 4s, 3p, 12, 12, 14, 14 plus 6, 14 plus 6, how many? 14 plus 6 equal to 20, right? 14 plus 6, 20. So 20. Then we have 4p, 3d, 4p, right? So 4p is 6. Then we have 3d, 3d, 1. Look, this is creating problem. So we'll use the second method to write the electron configuration. It is easy, right? SS, PS, PS, then DPS. So 2, 4, 10, 12, 12 plus 6, 18, 20, 20 plus 7. So 27. So already we have written, we distribute 27 electrons per cobalt. So 1s, 2s, 3s, 4s, right? Then 2p, 3p, and D start from 3d. So this is the electron configuration of neutral cobalt element. So what will be the electron and would like to show you the orbital diagram for this. So this is 1s, right? 1s, then 2s, then 2p. Here we have 6 electrons, then 3s, 3s, here we have 2, then 3p, 3p, we have 6 here, 3p, after 3p we have 4s, 4s, 2, then we have 3d. D has 5 orbital, 1, 2, 1, 2, 3, 4, 5. This is 3d. So at first you have to place 1, 1, 1, 1. Then you have to 7. So you have to pairing up. So in cobalt we are getting 3 unpaired electrons, right? And look, so this is paramagnetic. So now I will show you how to write the electron configuration of cobalt using noble gas notation. You know that we have helium, then neon, helium, neon, argon, 36. Look, we have to find the inert gas or noble gas whose atomic number is just below 27, and this should be this. So neon, so you have to count 10 electron, 2, 4 up to this. This is neon. Then we have 3s2, 3p6, well, 10, 18. Look, we have helium, neon, argon. Argon is 18. So we have to select up to argon. Then krypton is 36. So you have to select argon. So 2, 4, 6, 10, then 12, then 12, then 6, 18. So up to this. So we have argon 18, right? Then 4s2, 3d7. Look, cobalt is a transitional metal and its valence electron is 7 plus 2, that is 9, right? The valency electron is 9 because for transitional metal we consider D subshell as part of valency shell. For transitional metal you will not get D10, you will get D like 1 to up to 9, right? So incomplete field of D subshell is considered as part of valency shell for transitional metal. So here valence electron is 9 and this is the noble gas notation. Okay. Look, if you want to write the electron configuration of any element like this way, then you have to draw this line. If you draw this line in this way, this will be wrong. So you have to draw this line like this way: 1s, 2s, 2p, 3s, and 3p, 4s, then 3d, 4p, like this way. You have to draw line from this side. So for cobalt, look, we have 1s, 2, then we have 2s, 2, then we have 2p, 6, then 3s, 2, then we have 3p, 6, then 4s2, right? And after 4s2 you have 3d 7. So you have to draw line from this way, right? Now I will show you how to write the electron configuration of cobalt 2 plus and cobalt 3 plus. So look, in cobalt 2 plus means you have to deduct 2 electrons from the neutral atom. So 27 minus 2, that is 25. These 2 electron will go from which subshell? You know that electron usually go from the highest energy subshell. Look, the n plus L value for 4s equal to 4 plus 0, that is 4, and 3 plus d, that is 5. So 2 electron should go from this 3d, but this is not the right case. At first we will consider the highest value of n. So here highest value of n is equal to 4. So for cobalt 2 plus, the 2 electron will go from, look, sorry, will go from this this 4s subshell, right? So this is the electron configuration of cobalt 2 plus. This is right. This is the electron configuration of cobalt 2 plus. So what will be the electron configuration of cobalt 3 plus? So you need to delete one more from here. So that is why here you have to remove electron from here. That is, here you will be 6. So this is the Now this is the electron configuration of cobalt 3. Okay, now we'll write the electron configuration of chromium. So look, chromium, its atomic number is 24. So we'll write SS, PS, PS, then DPS. So 24, 2, 4, 10, 12, 12 plus 6, 18, 20, then 24. So we don't need this. Now place number 1s, 2s, 3s, 4s. Then P start will be start with 2p, 3p, and D will start from 3D. So this should be the electron configuration of chromium, but this is but this is okay, but this is not the actual electron configuration of chromium, right? So you know that ds orbital can take maximum 2, and the half of 2 is 1. P orbital can take maximum 6, and half of 6 is 3. D orbital can take maximum 10, half of 10 is 5. So half filled and full filled sp d orbital are more stable, right? So look here, D has 4. So since it needs 1 electron to be stable, so it can easily take from 4s, right? So it will take 1 more, and 4s will lose 1. So thus this is the actually exceptional electron configuration, right? You can impose the explanation from here. D5 is more stable than D4, so it will be D5. So can you say me what is the number of unpaired electron in chromium? So if you draw the orbital diagram for this is 4s and this is 3D. 1, 2, 3, 4, 5, 3D. Look, in 4s we have 1, in 3D we have 1, 2, 3, 4, 5, right? So we have 6 unpaired electrons in chromium, but if you place here 2 and if you place here 4, then you have how many unpaired electron? You are getting just 4, which is the wrong. For chromium you have to place 1 more electron to the D subshell, right? Okay, now let's talk about the electron configuration of copper. You know that copper is an element whose atomic number is 29. So let us distribute SS, PS, PS, DPS, DPS. So 2, 4, 10, 12, 18, 20, 20, 29. Look, 1s, 2s, 3s, 4s, 2p, 3p, 3d. So this should be the electron configuration of copper, but look here we are getting D9. So the stable form of D subshell is D10. So it will borrow 1 from this 4s. So it will be like this 1 and here like 10, right. So this is the electron configuration of copper.